Yeah, the test exam 2 is in 16 days, Friday, November 18th. In between now and then, well, we've got various things coming up, including a Math and Computer Science Career Night next Monday, November 7th at 7 p.m. in CC 313, next building over, one floor up. It's the tiered room. You can get extra credit for coming. There will be a short alternative assignment to do for extra credit if you can't make it. It's extra credit for one or the other, not both. But that would be 5 points towards your homework score. You need to be on time and stay the whole time, and I will be there and be making sure people are there and staying awake if you are there. There'll be a sign-up sheet going around that you can sign up on, but I'll be there to see you as well. Yeah, you know, even if you're not a math or CS major, which I know some people are not math or CS majors, I would encourage you to come anyway, not just for extra credit, but just to see what life is like after Bethel. We'll have 3 panelists who will be there to answer questions. They are math and CS graduates, but they'll be there to answer questions that you might have about, you know, getting a good job and what life is like after school.
You know about how long it'll take?
Probably about an hour. Okay. They'll probably talk for about 30 to 45 minutes and then 15 to 30 minutes of questions. Okay. I will tell you the alternative assignment later when I figure out what it will be. All right, today in lectures A and B, I want to do a lot of examples. So we'll try to get through as many examples as we can. I think that's going to be better than doing theoretical stuff. We'll save that maybe for Friday, do some proofs. But just today we need to do lots of series examples, talk briefly about absolute convergence, and then lecture B, power series, interval of convergence, and radius of convergence topics, and as many examples as we can fit in for that too. All right, so let's just do a bunch. We haven't had this kind of problem in a homework assignment yet. And all these problems are pretty much going to be decide on convergence or divergence with reasons, though I might just verbally say the reasons instead of taking the time to write them down. And if possible, it will definitely not always be possible, give the sum when there is convergence. Definitely won't be always possible. And secondly, sum should probably be in quotes, because again, we can't literally add up infinitely many things, but we define what we mean to pretend we're adding up infinitely many things when we talk about infinite series. So here's an example. Let's start n at something other than 1 or 0. And I'm calling it n here. I've typically called it k. That's okay. Let's start at 4. So that's one thing that's new here. And another thing that's going to be new is I'm going to put the sum of two things inside here. Oh, let's put negative 2/3 to the n plus positive 3/4 to the n. Does this series converge or not? And if so, with reasons, and if it does converge, can you find what it sums to? If I got rid of one of those terms, do you think you'd recognize what to do? If it was just that. It would be geometric, and the common ratio would be negative 2/3, which is between negative 1 and 1, it would converge. If I got rid of that, it would also be geometric, but with common ratio 3/4. Still between negative 1 and 1, it would converge. This series has got terms that are the sums of the terms of the individual series. There's a theorem that says this series will converge as well. I'm not going to fully write those reasons out in words here, but let's start by just figuring out what these series converge to. They are geometric because you have this common ratio being raised to the n power I am starting n at 4, so it is a little tricky. It's probably best to go ahead and write out what this looks like so you confirm in your mind that it does look geometric, and you also see what the first term is. The first term occurs when n is 4, negative 2/3 to the 4th power. That'll be positive 16 over what would be 81. That will be the first term. 2 to the 4th is 16, 3 to the 4th is 81. Then you'd have plus negative 2/3 to the 5th power. It's an odd power, so you're going to get a negative sign. 2 to the 5th is 32. 3 to the 5th is 243. Let's write down one more term. You're going to get a plus because the next value again will be 6. Negative 2/3 to the 6th power will be positive. 2 to the 6th is 64. 3 to the 6th is going to be 729, etc. That will be geometric. You do need to multiply each term by negative 2/3 to get the next term. Negative 2/3 times that is that. Negative 2/3 times that is that. It is geometric. This common ratio, negative 2/3, does have an absolute value less than 1. It does converge. It converges to the leading term, 16 over 81, divided by the common ratio. 1 minus the common ratio. 1 minus negative 2/3 in this case. That's 16 over 81 divided by 5/3, which is the same as multiplying by 3/5. Get a little bit of cancellation here. Looks like it sums to 16 over, what would it be, 135? Is what this converges to. It's not the final answer though, right? We're after that series. What about the other piece? It's also geometric. Common ratio 3/4. Its first term is 3/4 to the 4th. 3 to the 4th being 81. 4 to the 4th being 256. It will be geometric. It's going to converge to 81 over 256 divided by 1 minus 3/4, which is 1/4. Dividing by 1/4 is the same as multiplying by 4. 81 times 4 it will be 324 over 256. That'll reduce, let's see, to 162 over 128, and then 81 over 64. Does that look right?
Yep.
Did I get it right? No mistakes as far as you can tell? I thought you raised your hand, sorry. So, there's a theorem that says now, if you take two convergence series and you create a new series whose terms are the sum of the terms of the original series, this new series will converge to the sum of those two series. And so this will converge to 81 over 60, let me write it as 16 over 135 plus 81 over 64. You get a common denominator, which would be pretty big here. Let's go ahead and see what this ends up equaling. 16 over 135 plus 81 over 64. Looks like this converges to that. 11,959 divided by 8,640. Could we check it with the summation button from the palette? Let's try it. N goes from 4 to infinity. Right here. Oops, don't want that. Use parentheses. We've got negative 2/3 to the n and a plus 3/4 to the n. I hope I didn't make a mistake. I hope it's the same thing. Yeah, it is. So I said the reasons verbally, I'll say it again quick. These two series are geometric and converge, and you can figure out what they converge to. Therefore, this one converges and converges to the sum of what those series converge to. Let's do another example. Let's do one of your homework problems, actually. One that was kind of tricky, involving factorials. There we go, remember this one? Whenever you've got a series involving factorials, almost always the best thing to try is the ratio test. At least, well, you could try the divergence test first. If these terms that you're adding don't go to 0, then it has no chance of converging. It's still a little tricky because it's involving factorials. Maybe we should just try to look at some numerical evidence and see whether we believe those terms go to 0 or not. I could make a table of values of the terms that are being added. So that's n factorial squared divided by 2n factorial, 2n quantity factorial. And let's numerically approximate these. They're going to get, let's get some numerical approximation for those. Looks like they're probably going to 0. That's not a proof, but it looks like they are. So the divergence test does not apply. It could converge. It might still diverge, the series, but it's possible it could converge. We need some other test. And once again, like I just mentioned, the ratio test is typically the best thing to use with series that involve factorials. Here's what it looks like in general as you do this calculation, if you can. See if you can calculate this limit. The absolute value signs should be there in general, and I guess as a habit you should put those there to start with. Even though in this case the terms are all positive, so you really don't need the absolute value signs there. In fact, I will get rid of them in the next step. What's a sub n plus 1? Well, this is a sub n right there. To find a sub n plus 1, you just use the same formula, but you replace n with n plus 1. So we will get n plus 1 factorial quantity squared over 2 times n plus 1 quantity factorial. That is a sub n plus 1. Do you see that? Compare here. With this, I'm just replacing the n there and there with an n plus 1. Being careful to use parentheses, for example, right there. Divide by an divides by n factorial squared divided by 2n quantity factorial. I really could have just skipped to the next step. When you divide two fractions, you got to multiply times the reciprocal of the bottom. Although, in the interest of trying to simplify as quickly as possible, I'm guessing based on what we saw last time that it would be good to write n plus 1 factorial as n plus 1 times n factorial. That probably is a good idea. So I'm going to get n plus 1 times n factorial squared. And this is 2 times the quantity n plus 1, which is really 2n plus 2 factorial. That would be the same as 2n plus 2 times 2n plus 1 times 2n quantity factorial. And that's going to end up canceling with that one. This would be good to write. Go ahead and write it. 2n plus 2 times 2n plus 1 times 2n quantity factorial. Multiply times the reciprocal of this one on the bottom. So I have a 2n factorial on top and an n factorial squared on the bottom. The 2n factorials do cancel. This is the same as n plus 1 squared times n factorial squared. You can square both factors individually, then multiply. And so this n factorial squared will cancel with this n factorial squared. What's left over? We did not cancel the n plus 1 squared there. And we also did not cancel the 2n plus 2 and the 2n plus 1. So we get n plus 1 squared, 2n plus 2, 2n plus 1. That's a rational function of n where the degree of the top and the bottom is 2, the same. And you should know that in any such situation, as n goes to infinity, the limit will be the ratio of the coefficients of the highest powers. What's the highest power? Here it's going to be n squared. What will its coefficient be? It'll be 1. Here the highest power is n squared 2 as well, and the coefficient will be 4. 4n squared comes from first times first there. Therefore, the limit of this rational function as n goes to infinity has to be 1/4. You should have gotten 1/4, which is less than 1, and therefore, by the ratio test, this original series converges. Okay, it does converge.
So in the homework, they told us what test to use in future homeworks or in like an exam. You have to figure out what test to use.
Possibly, yeah. But I did just say before we started this example, pretty much any time you have factorials, the ratio test is the way to go. Except maybe check the divergence test first. I mean, as an extreme example, you definitely don't need to use the ratio test for that. That definitely diverges. Okay. The terms definitely do not go to 0. As an extreme example of that. Okay, so in general, if it's not obviously geometric, the divergence test is the first thing to look at. But then if the terms do go to 0 that you're adding, then you need some other test to see if it's converges or not.
How did you get the 2 times n plus 1 and all that factorial to equal the 2n plus 2 times 2n plus 1 times 2n?
This right here?
Yeah, how did you get that from the thing before?
First of all, well, it was 2 times the quantity n plus 1 factorial. I multiplied the 2 through to get 2n plus 2. And then it's got a factorial there. That's the same as 2n plus 2 times 2n plus 1 times 2n factorial. If, for example, 2n plus 2 happened to be 22, you'd have 22 factorial is 22 times 21 times 20 factorial. Okay? If we had considered a similar series, except with these switched around, imagine switching those around, having the n factorial squared in the bottom and the 2n quantity factorial on top, this calculation would have given us a limit of 4, which is bigger than 1, and that series would diverge. Though because of this evidence, the divergence test would evidently show that the terms don't go to 0, and therefore the divergence test would imply the series diverges as well. All right, another example. Sum n goes from 1 to infinity of n e to the negative n. you have any intuition about whether this converges or not? Do you have a good guess? It's good to try to develop that. Well, you can be wrong.
I would guess that it would diverge
And why do you guess that it diverges?
because well, I know at first it would decrease because E is greater than 1. So your first value would be 1 times 1 over E.
Which should be around, I think, 0.3 something.
Yep. But then as E is because E is on the bottom of a fraction and it's exponential as opposed to arithmetic, so the exponent will grow faster than the number n. So that's my guess that it
Okay.
will converge.
Okay, you're going to change your guess, and the new guess is correct, converge.
I meant to say converge from the
Okay.
beginning. That I was thinking convergence said diverge.
Okay, that happens to me too, by the way. Don't worry about it.
I'm
It
not
happens to
lying.
me. It happens to me all the time. Yeah, e to the n, you're right, your logic is right. E to the n is exponential growth,
Yep.
whereas this is linear growth. Exponential growth is fast growth. This fraction not only goes to 0, but it probably goes to 0 very fast. Fast enough to make the sum probably converge. How could you verify it? Well, first we should check the divergence test. Do these terms go to 0? And yes, they would. You check out evidence. So we do need similar tests. I believe the ratio test would work here. Let's try the ratio test. Oftentimes the ratio test works when n is in an exponent as well. Again, we can get rid of the absolute values. These quantities are both positive. Even though you've got the negative power there, it's still positive quantity. Try that. What does this simplify to? Let's see. This is the same as e to the negative n times e to the negative 1. The e to the negative n's will cancel, giving you a limit as n goes to infinity of e to the negative 1 times n plus 1 divided by n. The e to the negative 1 is a constant that can be put in front of the limit, or you can say this is a rational function of n, degree of the top and bottom are the same, 1, highest power of n. Coefficient of the n on the top is e to the negative 1, coefficient of the n on the bottom is 1. This limit is e to the negative 1, 1 over e, which is indeed less than 1. It will converge by the ratio test. If you look at this and imagine changing the n to an x, x e to the negative x, that's a function that's definitely possible to integrate. You could try the integral test instead. Does this improper integral converge or not? With this being the f of x, you would need to verify that function's non-negative, and it is, and decreases to 0. Actually, we don't know for sure if it's decreasing over the entire interval from 1 to infinity. But certainly past a certain point it is. I mean, you can take its derivative if you're not sure. If you want extra verification of when it starts decreasing, with the product rule, its derivative would be e to the x plus x e to the x. E to the x times x plus 1. The only critical point of this is at negative 1. Excuse me, sorry, that's a typo. Thought that didn't make sense. Forgot my negative x there. The only critical point of it is a positive 1. And that critical point would be a maximum. The graph looks like this. Maximum is reached at 1, and it decreases thereafter, and it does decrease to 0, which is what we told you to verify that. So the integral test would apply. It would be fine with me if you just made the graph with your calculator. I'd probably say you can make the graph with your calculator.
So, but how does getting the derivative help us to get the antiderivative of that function?
It's not. I'm just verifying the derivative helps me verify the graph looks like this.
Oh, okay.
So that over here the function is positive decreasing to 0,
Oh.
which are conditions in the integral test.
Ah, gotcha.
Anyway, you could do the integral. I don't want to finish this integral for sake of time. You'd use integration by parts. It does converge. And that would be another way to verify that this summation converges. Can we find its value? And could we find the value of the other one? I guess I forgot to try that. Possibly, we could find its value, but I'm not positive offhand how to. It's not geometric. I mean, if the n were not there, it would be geometric. It's n times something that comes from a geometric series, and I believe you can find the sum of such series. I'm just forgetting how to offhand. Let's see what Mathematica produces for it, if anything. I think it will give an answer. Yep, there's what it converges to, evidently. What about the other one? Does that converge to anything recognizable? Possibly again. By other one, I mean this one here, where these are the terms. Although my guess is if this one converges to something, it's not something you're used to. I'm guessing it's going to involve a special function. One of those non-standard functions, perhaps like ERF or something. I might be wrong. Let's see. Okay, oh, it's an ordinary looking number. I mean, kind of strange number, but it doesn't involve ERF or anything. It doesn't involve the error function like I thought it might. There are all sorts of special functions. There are Jacobi functions. There are Legendre functions. Okay. Mathematica's got them all stored, and sometimes you might get something strange like that. Elliptic functions is another example. If you do, you just got to realize, okay, that's a function I've never heard of before. Okay? Mathematica is giving us the answer for this as sort of an ordinary number, though it does involve pi, interestingly enough. Again, pi showing up in weird places. Okay? Completely unexpected. There's a pi. That's part of the intrigue of math, by the way. Why is there a pi in there? Isn't that weird? There's no circles anywhere. How can there be a pi? But there it is. That's the intrigue of math. All right, what else? Other examples? Time, almost break time yet. Well, let's go another 5 minutes or so. This series does not have all positive terms. When n is 1, negative 1 to the 0 power is positive 1. Divided by square root of 1 is 1. When n is 2, this becomes a first power there, and negative 1 to the first power is negative 1. Divided by square root of 2, I get minus 1 over square root of 2. When n is 3, this becomes a 2. Negative 1 squared is positive 1. I get a plus 1 over square root of 3. When n is 4, this becomes negative 1 to the third power, so I get a minus sign, and then a square root of 4 on the bottom, which is 2. Plus 1 over square root of 5, minus 1 over square root of 6, plus 1 over square root of 7, minus 1 over square root of 8, plus 1 over square root of 9, which is 1/3, etc. Does this series converge or not? Based on what we talked about at the end of class on Monday and what you did, I think, had one homework problem about. Do you know what I'm talking about? As far as whether it converges or not? You know the answer? It was briefly discussed on Monday.
I forget what it's called, but it's something like the alternating function hypothesis.
Alternating series test.
I think this one did converge.
This one does. It does satisfy the conditions of the alternating series test. The form of a series in the alternating series test is a series that looks like this. The a-n's are actually not the terms. It's the -1 to the n minus 1 times the a-n. That is the nth term. If you write this out, it's a1 minus a2 plus a3 minus a4 plus a5, etc. The a's themselves in this expression are taken to be non-negative, actually positive, and decreasing to 0. The book writes it like this. But this is true for all n, which means the a's are decreasing as n increases. And moreover, that the limit of the a-n's is 0. In that situation, the alternating series test says series like this do converge. Does our example fit that? Yeah. A-n here is 1 over square root of n, which is 1 over n to the 1/2 if you prefer. That is a quantity that's positive and decreasing as n increases. It satisfies this, and it does go to 0 as n goes to infinity. Therefore, by the alternating series test, this series does converge. Though I will say it converges very slowly. Let's look at the partial sums of this thing. I guess I'm going to use a k here instead of an n. If we look at the partial sums of this, make a table of values, let's approximate these to say 10 decimal places as n increases. That's S1, the first partial sum, which is the same as A1, the first term, 1. There's S2, 1 minus 1 over square root of 2. Square root of 2 is about 1.4. 1 over square root of 2 is about 0.7. So this is approximately 1 minus 0.7. There's the third partial sum, fourth, fifth. These numbers bounce up and down, you can see. They get high, then they go low, high, low, high, low, high, low. But they do get closer and closer together as you keep increasing. So very slowly. This could be highlighted even better if you manipulate. We don't need to make the whole table though. So we're looking at, let's go out to 20 decimal places. We're looking at the partial sums as the number of terms increases. Is it settling down to something? Well, if it is, it's very slow. Let's let n go to 10,000. Still going very slow. If it is converging, it's very slow. Let's try 100,000. It might bog Mathematica down a bit here, but let's try it anyway. Okay, it's bogging down. It seems to be converging to something around 0.6. Can I do a limit of S of n as n goes to infinity? Can I calculate it? I'm not sure. It looks like it's having trouble with this. Oh, there we go. There's some special functions. Zeta, our friend Zeta that we talked about the other day with the Riemann hypothesis. the zeta function comes in. And what's this include singular term arrow false? I have no idea what that is. Actually, I see the limit there still. So it's like it's actually just calculating a partial sum of this instead of the full infinite sum. It doesn't, it's not able to do it every time. But the sum does converge, just very slowly. Let's take a break. We'll start again in 3 minutes at about 11:49.